So today we'll be going over friction and how to solve problems that involve friction. So let's go ahead and use an example for instance, such as this. And we have this box with weight W acting about the center of mass of this box. Now let's say we also have a force P being applied to this box. Now, since we have a box going to be sliding across a surface, that means we have friction involved because we have 2 points of contact. We have the box contacting the surface itself that will be sliding across, and that's going to involve friction. And normally we have a normal force, let's call it N, right? Because we have it reacting to the weight of the box. Now, how we represent the frictional force is actually the frictional force is always opposing the motion. In this case, since there's a force P going towards the right, the frictional force will be acting opposite. So let's call this lowercase f for the frictional force. Now, as you could already see here, because we have these two components, the normal force and the frictional force, we could actually draw a resultant force as well as with its appropriate angle. So here's the resultant force and here's the angle phi here. But for the most part, for now, we don't need to focus on these, just the frictional force and the normal force. So a few things you need to know is there is what's called static friction, as well as kinetic friction. So here are the equations. We have the static force being equal to some coefficient mu of s. This is known as the coefficient of static friction times the normal force. So this is the equation for the static friction. And for the kinetic friction, is equal to the coefficient of kinetic friction times the normal force. So here are the two equations that you're going to be using. Now the difference is for the static friction, you use it when there is no motion in the object. That means the object is stationary or static. However, if there is motion, you're going to have to be using the kinetic friction formula. And the only difference here is between the coefficients. So there's a difference between the coefficient of static friction as well as the coefficient of kinetic friction. And I think it's a lot easier to explain this with a graph. So here we have this graph being plotted of the frictional force for the vertical direction. For the horizontal is the force being applied to the box P. Now when it comes to the static friction is when there is no motion of that box. So as you can see, the frictional force steadily increases as P increases up to a maximum point here. Now at this very point between where there's no motion and motion, this is what's called impending motion. It's at the point right before there's any motion, and this is where you're going to get the maximum static frictional force here, F of S. Right after you exceed the maximum static frictional force, then afterwards you get motion. The box starts to move, and that's where your frictional force decreases to that kinetic frictional force, and as p keeps on increasing, it starts to accelerate more, then the friction starts to decrease as well. Now this is the main difference between the static and kinetic frictional forces. You're gonna actually have a higher force right before there's any motion, but once the object starts to move, that's where the frictional force decreases, and which is called the kinetic friction, and that's because there is motion, mainly because there's now momentum of the object that's moving. So it's a little bit counterintuitive at first. The static frictional force is going to be higher, then if there's motion, it's always going to decrease, and that's the kinetic. Once there is motion, you have the momentum of the object move. One thing to keep in mind as well when it comes to the normal force, it does not necessarily mean it's going to be applied right at the center of mass where the W is. It's going to be applied somewhere along X location here, and you could always solve for it just using the sum of moments to solve for where this normal force is being acted upon on the object itself. One thing that's important to remember is to Remember that the frictional force is always opposite to motion or to any potential motion, such as the P. If it's not sufficient to move the box, it's still going to be acting against the force P here. So let's go ahead and do an example. So for this problem statement, we actually have a ladder, and the ladder has a uniform weight of 80 pounds and rests against a smooth wall at point B. If the coefficient of static friction at A is equal to zero point 0.4, determine if the ladder will slip. So the coefficient of static friction is equal to 0.4. Now we need to determine if at this point will it slip given the angle theta equal to 60 degrees. So let's go ahead and draw the free body diagram of this ladder. So here's the free body diagram. At point B, we just have the reaction force, the normal force at point B. We have the weight of this ladder being 80 pounds, and since it was uniformly distributed, then it's safe to assume it's right at the center of mass, right half at the half point of the ladder, so 7.5 feet from the bottom. And at point A, we have that frictional force Fa and the normal force Na, and we have the ladder being at 60 degrees. So here we could just do a simple sum of forces along the x and along the y direction to get the reaction forces here. So let's go ahead and do that. So first up is the sum of moments with respect to point A is equal to 0. So we have this normal force NB times the perpendicular distance to point A. So we just get the basically the vertical component of that. So it's 15 feet times sine 60 degrees. Then we have the 80 pounds force also having a moment about point A, but it's negative, so it's negative 80 pounds times 7.5 feet times cosine 60 to get this horizontal distance, which is perpendicular to this force to get the moment. So now let's go ahead and solve for the normal force at point B. So we have NB being equal to 23.09 pounds. So let's do the sum of forces along the x direction. So for the sum of forces along the x, we only have the frictional force at point A, Fa, take away the normal force at point B. So we have Fa, the frictional force at point A, being equal to 23.09. So the frictional force at point A is 23.09 pounds. So now that we found the frictional force, now the question is does this mean that the ladder is slipping, meaning there's motion? Does it mean is impending motion or about to slip, or is there no motion at all? Is it just static? So this is where we actually solve the maximum static frictional force, which is basically the coefficient of static friction times the normal force at point A. So first we have to solve for that normal force NA. So to do that, let's go ahead and do a sum of force along the y direction. And we see that the normal force at point A is 80 pounds. So let's go ahead and solve for the static frictional force, which is the coefficient of static friction times this normal force at point A. So we get the static frictional force is equal to mu A times Na is equal to zero point 0.4 times that 80 pounds. And so we have the static friction being equal to 32 pounds, and this is what value that we're going to be using to determine whether there is no motion or if it's going to slip in this case. Now, one thing that may help you to visualize this is that graph that I initially drew in the beginning. Let's go back to that. So in the region of that there being no motion, we see that the maximum, let's say this is the maximum static friction, will be at this peak right where motion is impending. Now, if we have a friction that we just solved for being less than that maximum, then most likely no motion has occurred. And that's actually what we see in the problem that we just solved right now. We see that the frictional force Fa that we saw is less than the maximum static friction, which means that there is no motion. Therefore, the ladder is not slipping. So that's how we determine that the ladder will not slip in this case, because the frictional force that we solved for in using the free body diagram is actually less than the maximum. So 23.09 pounds is less than 32 pounds. That means there is no motion, and you saw the region that we're in within that graph itself. So let's go over the three cases for the frictional forces. So for case one, there is no motion. That means the frictional force that we saw for in the problem is less than or equal to the static frictional force, or if you want to say the maximum, which is equal to the coefficient of static friction times that normal force. So this is case one, where the friction that we solved for is actually less than the static frictional force. For case two, there is impending motion. That means that the frictional force that we found is exactly equal to the coefficient of static friction times that normal force. This is where it reaches that maximum point right before there's any motion. That means it's impending motion. That's case two, right? Where the frictional force is exactly equal to this. And finally, for case three, there is actual motion, and that means the frictional force is equal to the kinetic friction, which equals to the coefficient of kinetic friction times that normal force. And so these are the three cases: when there is no motion, when there's impending motion, and then when there is motion. These are the equations to be using. So let's go ahead and do another problem where we're going to actually be determining whether there is motion or whether the object is stationary. So for this problem then, we have the crate has a weight of W equal 150 pounds, and the coefficients of static and kinetic friction are zero point 0.3 and zero point 0.2 respectively. Determine the frictional force on the floor if theta is equal to 30 degrees and P is equal to 200 pounds. So we're given the coefficients of static and kinetic friction being zero point 0.3 and zero point 0.2. So remember, when we have a box or any object, we represent the weight of it at the center of mass. In this case, is 150 pounds, right? Being directed here. Now we're being asked to find the friction force on the floor itself. So remember, we have that normal force, let's call it N, and the frictional force, which is always opposing any motion or impending motion. So in this case, we have a force going towards the right direction. So we're going to have that going opposite of the right, going towards the left, and the friction. So we're going to go ahead and solve for that frictional force first. So first, doing the sum of forces along the x direction. So we have the frictional force at the surface being 173.21 pounds. Now let's go ahead and solve for that normal force, which is the sum of force along the y direction. And so the normal force is equal to 50 pounds here. So now that we solved the unknowns here, which is the normal force and the frictional force at the surface, let's go ahead and see what the maximum static frictional force is, which we already know the equation is the coefficient of static friction times that normal force. So the maximum possible static frictional force is 15 pounds, and we see that that's actually above that maximum friction of the static. So remember the cases. For case one, when there is no motion, the frictional force is less than or equal to the static frictional force, and we see that that's not the case. It's not, and it's also not case two. It's not even case two where the force is exactly equal to the static frictional force, which means it must be case three where there is motion, and that means the the equation that we need to be using to solve for that frictional force is actually the kinetic frictional force, which is the coefficient of kinetic friction times that normal force. So the actual frictional force at the surface is the kinetic friction, which is 10 pounds. So this 173 pounds is actually incorrect. Now, the main reason being, since we determined that this box is actually in motion, that means it's invalid for us to use the static equilibrium equations, because remember, the equations that we're using are equal to zero because all the forces are canceled out, because we're assuming that the object is stationary, it's static. But in this case, since there is motion, this equation does not hold, which means In this case, we had to use the equation for the kinetic frictional force, which is equal to 10 pounds. And so this ultimately is our answer. The frictional force at the surface is 10 pounds. So when it comes to these problems, it's kind of a little bit different because you have to double check, right? You could do all these formulas you saw for the appropriate values, but you have to compare it to these other equations, which is the frictional force equations, to be able to determine what the actual situation is, whether there's motion or whether there isn't, to determine what appropriate equations to apply and to actually get the correct value. So this is one thing that's a little bit different. Um, it takes some getting used to, but it's actually pretty cool to be able to kind of double check your answer with other formulas to see what's going on in the situation. In this case, whether there's motion or whether there isn't. And since we determined there was motion, the actual frictional force that we initially saw for the sum of forces along the x was incorrect because the underlying assumption was that the object was stationary, which is not. So we had to use the kinetic frictional force equation here. And so this is how you solve problems that involve friction.